The next topic that we'll be covering today is that of the fundamental frequencies of helical springs. So, whenever springs are used in applications where they would be loaded and unloaded at a relatively fast pace, at least few hertz or few tens of hertz, then in those cases it must be made sure that the excitation frequency is nowhere close to the fundamental frequencies of the springs. So, alright, so in order to understand what's the relation between the fundamental frequencies of springs and the spring parameters, consider a small section of the spring of length dx. At one end, it is being subjected to force F and deflection U. At the other end, force F plus dF and the corresponding deflection U plus du. Now, from the free body diagram, applying the momentum balance, we can write down that the net force acting on the spring in upward direction would be equal to the mass of this particular length dx, which is mass per unit length multiplied by dx, into the acceleration of this particular section. Now, W over here is the weight of the overall weight of the spring. L is the current length between the end plates, and G is the acceleration due to gravity. So W by G gives you the mass of the spring, and mass divided by length gives you the mass per unit length of the spring. Now, well, we know that the force that we apply on the spring is related to the deflection y through the relation F equals to ky. Now this can be rewritten as F equals to k into L into y by L. Now we can use the first expression when we are dealing with static conditions and the spring is deforming uniformly. But when we have a dynamic condition, then in that case the spring deformation is different at different points, and the force is related to deflection through the relation F equals to KL into du by dx. So for a small section of length dx, du is the change in length of that particular section. So, well, based on the free body diagram, now we can write down the moment balance equation as d by dx of df, which is kl into du by dx is equal to w by gl into d square u by dt square. Now, rewriting this relation, we get this. Assuming that k does not change with length. So this is for a spring with uniform pitch. Now, solution to this particular equation is of the form u equals to u naught into sine m pi by l alpha t into sine m pi x by l. So this is an equation for a standing wave, and with alpha equal to square root of kg by w into l. And through this we can find out the angular frequency for the spring when we have two flat end conditions happens to be m pi into square root of kg by w. So the natural frequency is equal to angular frequency by 2 pi, which is m by 2 into square root of kg by w. Now the fundamental frequency, which is the lowest frequency for two fixed end conditions, can be obtained by taking m equals to 1 or f equals to 1 by 2 into square root of kg by w. So this is the relation that you need to remember whenever you're dealing with two fixed end conditions for the spring. Now if one end is fixed and the other is free, then the fundamental frequency is half of what you get for two fixed end conditions. Now the weight of the active part of the spring is given by this particular relation, where gamma is the specific weight. Now what the design guideline states is that the fundamental frequency for the spring should be at least 15 to 20 times that of the operating frequency for the of the excitation frequency, okay, in order to avoid resonance.